Hey guys, Mr. Betts here. We've spent the last two units in calculus, so unit 2 and unit 3, talking about how we take the derivatives of functions. And now in this unit, we're going to look at how we can actually use those derivatives to help us solve real life problems. So I want to start by kind of talking about what we've been doing with the derivatives. So we've had a function, might be called f of x. So we might have f of x equals something with x's in it, or it might be y equals something with x's in it. And when we take that derivative, we interpreted that as an instantaneous rate of change. But from a graphical context, we've been interpreting that as the slope of a tangent line. So the slope of this line right here is going to be given by the derivative at that point. So we indicate the derivative either f prime of x, or we might say dy dx, which in the context of real world problems, I actually like the Leibniz notation, that differential notation, a little bit better. So remember, the dy dx represents a change in y with respect to a change in x. But what we're looking at is a very, very small change in y with respect to a very, very small change in x. So we're looking at a limit as those changes approach zero, and that gives us a slope of a tangent line. So if we think about how this might be applied if the function isn't y in terms of x, but say profit in terms of the number of thingamajigs that are manufactured by some company. So this is something where we might have a function that looks exactly the same, but now this function represents something in the real world. So the derivative is also going to represent something in the context of that problem. So first of all, we would use notation that's the same, p prime of n, or instead of dy dx, we no longer have a y-axis, but we have a profit axis. That's our dependent axis, the vertical one. So we would have dp instead of dy. So that's a small change in profit divided by the horizontal axis is going to give us a change in a number. So dp dn is still representing the slope of a tangent line in this coordinate plane, but now dp dn has a meaning in the context of this problem. And that meaning becomes a little bit more obvious when we look at the units that we would get. So keep in mind this dp is a change in the profit. So that's going to be measured in dollars. And dn is a change in the number of thingamajigs in this case. So that's going to be measured in units. So when we take a derivative, we're taking dollars divided by units, or we would say dollars per unit, or I'll say dollars per thingamajig. It's a real thing, by the way. Not really. So dollars per thingamajig actually has a meaning. In this case, it's telling us our profit in dollars per thingamajig that we're manufacturing. And the fact that in this case, that slope is positive tells us the derivative is positive. That means that our profit is increasing per thingamajig that we make. If we look at what's happening in the section here where the slopes are actually negative, that would probably be a bad business option to at least cut off production in that range, because we're losing money per thingamajig we make. Maybe it's costing us more money than we're making when we sell them. I'm going to look at this from a few different contexts here real quick. So instead of profit and thingamajigs, we have volume and time. So we might have the volume of, say, the amount of water in a container. So the volume is changing. Maybe we're adding and draining water to the container. And so the derivative of our volume with respect to time, we could represent v prime of t, or we could say a change in volume with respect to a change in time. So dv dt is going to be how we represent that derivative here. And the units, again, are going to be the volume units, so cubic centimeters per. So really we're dividing by the time units, minute, but we can read that cubic centimeters per minute. And again, a positive value at this point is telling us that the volume is increasing a certain amount of cubic centimeters per minute. If the slope here were negative, that would tell us that the volume is decreasing at a certain volume per minute. So this is telling us how fast this quantity, this volume, is changing at any given time. So an instantaneous rate of change of volume. Looking at another example here, we have velocity of some object measured with respect to time. So motion problems, so where we're dealing with position and velocity and acceleration, they're going to be a pretty common application that we're going to do. And so in this particular case, if velocity is a function with respect to time, then the derivative v prime of t could also be written a change in volume with respect to time. And since volume is measured in meters per second and time is measured in seconds, then we get units that are going to be meters per second. So that's the volume units, and then per second. So it's not immediately obvious what this is going to mean. So meters per second tells us how fast something is moving. So meters per second is telling us how fast it's moving. So the velocity, how fast that velocity is changing. So in physics, a lot of times we will simplify the writing of this and saying it by saying meters per second squared. Square seconds are not real units, but when we say meters per second squared, what we mean is meters per second per second. So it's telling us how fast the velocity in meters per second is changing with respect to time each second. So in this case, the positive slope of the tangent line is telling us that the velocity is increasing. And we can see that on the graph. If we move from this point to another point along the graph, we can see the velocity has increased over that time. So this derivative is telling us that the velocity is changing, in this case increasing by a certain amount. We might see a population graph. So population of deer, so just the number of deer given in years. So on any given year, we can see what the population of deer is in, say, a particular forest or something. Then the derivative, p prime of t or dp dt, is going to tell us how fast the number of deer is changing per year. So the positive slope here tells us that the population is increasing a certain number of deer per year. And we can see again that if we move to the next year, that population is in fact greater. So the slope of the tangent line is telling us at any given moment what is the rate of change of that population. I do want to take this one and look at it in the context of a second derivative. So remember, second derivative is the derivative of the first derivative. So dp dt is the first derivative measured in deer per year. So it's telling us how fast that population is changing. The second derivative, so I'm going to say the derivative with respect to time of dp dt, which if you remember the second derivative notation, we write like this. So this is telling us how fast this quantity is changing with respect to time. So dp dt is deer per year. And then that's changing each year. So it's going to be deer per year per year. And from the physics context, we could say deer per squared year, deer per year squared. Again, a square year doesn't mean anything, so I'm not a big fan of doing that, but it's not wrong to do that. But essentially what that's saying is this slope right here tells us how fast the population of deer is changing at this time. But if we move a little bit further along, not only has the population increased, so the population went up, but the speed that the population is increasing, the slope of the tangent line, also increased. So the slope here, which represents how fast the population is changing, the slope itself is actually increasing, so the population of deer is growing faster from one year to the next. So the second derivative is telling us how fast the first derivative changes, and the first derivative tells us how fast the population changes. So in the context of these problems, the second derivative actually has meaning also. So big idea here, the units on a derivative are going to be vertical units divided by horizontal units. So regardless of what the model is, whatever these units are here and whatever these units are here, we divide vertical by horizontal and we get the units for the derivative. And so that in the context of a problem is going to tell us how fast some quantity is changing, an instantaneous rate of change at any given time.